continuing our webinar series. Today we have Luca Visinelli. Luca earned his PhD from Utah University in 2011. Since then, he's been a postdoc at several institutions. Most recently, he was at Nordita, Stockholm University, Uppsala University, and now he's at University of Amsterdam, right, Luca?
Yeah.
So today he's going to talk about astrophysics with axion stars and mini-clusters. So it's a pleasure to have you here today, Luca. Please take your time.
Okay. So thanks for the introduction and for allowing me to give a presentation today. Yeah, my name is Luca. I'm a researcher at Grappa, University of Amsterdam. This is my title for the presentation. I'll discuss how we can gather information from radio or gravitational waves using cosmic axions, so taking some indirect approach, detection approach. The outline of my talk would be roughly within minutes to give a presentation of what generally a dark matter candidate is, why the QCD AXIOM is a good dark matter candidate. And I'll spend 15 minutes on radioastronomy with Axion Miniclusters. And then if there is some time left, I'll spend the last 5 to 10 minutes talking about gravitational waves from axionic strings. So, well, we know that we had overwhelming evidence for the existence of both dark matter and dark energy. The most stringent confirmation of this comes from studying the lambda CDM data. So the data that comes from Planck that fit a lambda CDM cosmological concept called dark matter model, in which we have the evidence for distinct components, that is dark energy that nowadays takes around 70% of the energy pi, and a dark matter component which is essential at recombination, is essential to reconstruct the peaks that we observe, and nowadays takes about 1/4 of the pi. I will focus on the matter part of this pie chart, so on the ordinary plus dark matter, of which the dark matter takes 85% of the share total. So we can say that 85% of the matter is dark nowadays, while the rest is in gas and in stars. There is other evidence from the existence of dark matter that spans different ranges of scales. The historical one has been the rotational curves of galaxies. We know that if we just consider the luminous amount of matter in a galaxy, we can predict some curve, some velocity curve, which does not match what we actually observe. So the dashed line here on this chart to the left says what we should see in the motion of the stars, depending only from the luminous matter that we see, while the dots and the solid line here are the actual observation that basically say that we are missing something, either a modification of Newton equations or dark matter. We now tend to be more in favor of a dark matter interpretation because of the bullet cluster or other clusters of galaxies that collide with each other, since we see the potential well of the dark matter that basically passes through the two clusters of galaxies and created two distinct wells, which is something which is difficult to reproduce in terms of just modified gravity. Nevertheless, it's always good to be wide in the range of possibilities. There is also, as I said, the strong and important evidence of the dark matter. The dark matter was already deepening the potential well during the recombination. The map that I've put here is lensing that we can reconstruct from the CMB data. So this is the dark matter column density that we see in the sky. Let's get now back from the problems in cosmology and astrophysics, and let's focus for a second on particle physics. So for this, I want to introduce the Axion and show why this is a dark matter candidate. But in order to do this, I have to first get back to particle physics and mention that the standard model contains what's known as the strong CP problem in the QCD sector. So the Lagrangian for the standard model allows for this piece, which is CP violating, in which appear the electromagnetic counterparts of the gluon field. This is G mu nu. So this is the gluon tensor field. The strong force coupling and overall factor theta bar, which controls the matter-antimatter asymmetry in QCD. So this term that I wrote, of the Lagrangian that I wrote here, is responsible for the appearance of CP violation in QCD. In particular, this term gives rise to a neutron dipole, electric dipole of the neutron. So you would see the neutron oscillating in an electric field, which is something that you can go in the laboratory, measure, and you don't observe. So from this non-observation of CP violation in nature due to this, due to the QCD sector, we can put an upper bound on this parameter theta of the order of 1 part in 10 billion. Nevertheless, this parameter theta can very well be of order 1. We expect it to be of order 1, and so we are left with this so-called strong CP problem that plagued the physics in the 70s. Why this parameter, which we expect to be of order 1, takes such small values in nature? It could be that there are different solutions. The Axion solution is the most elegant and viable to date. So this was introduced by Pechet and Quinn. I would like to mention that Pechet passed away yesterday. And together with Quinn, they proposed that the strong CP problem can be solved by promoting this parameter theta to be a field. And then it's the dynamics forces this field to be close to 0 and to lead to the non-observation of the CP violation, as we actually see, observe in the laboratory. So this is a classical field which you can quantize, and this actually leads to the idea that there is a new particle associated to the Pechet-Quinn mechanism, which is called the Axion. So my theta is actually can be actually thought as a quantum of a new particle, the Axion here, A, which make along with the gluon fields here, G, a dimension 5 operator. So in order to have consistent Lagrangian term, I have to divide these pieces by a new scale factor, which is called the Axion energy scale, which was originally thought to be related to the QCD sector, since the Axion itself is related to the QCD. But current experiments, which I will mention later in the talk, actually constrain this FA to be above 10 to the 9 GeV. So since the axion mass is inversely proportional to this parameter f, the higher f, the smaller m, and now for a value of f above 10 to the 9 GeV, we expect an axion of mass below order 10 to the minus 2 electron volt. So an extremely light particle, which could very well be well below in mass, well below to the mass of the neutrino. Nevertheless, this particle can be produced as a cold dark matter candidate. I'll explain in a second why. So we expect the axion photon coupling to also arise through this axion photon Feynman diagram. This is an anomalous diagram. And this allows for the search in laboratories and the search through conversion of photon into axions and axion produced in stars, sun, and in other stellar objects. This is why we can place bounds on this particle, on these models. So here on the y-axis, I've put GA gamma, so the axion photon coupling, in units of inverse GeV. Whereas on the x-axis, there is the axion mass in electron volt. The yellow band here spans different theories for the axion. So different embedment of the Pechequin model into the standard model, which give rise to different coupling of the axion to new fermions in the theory, and then to different values of GA gamma as a function of the axion mass. What you actually discover when you compute this Feynman diagram for the axion photon coupling is that GA gamma is directly proportional to m, to the axion mass. This is why you have here straight at 45 degrees. Each line is a different theory in which you have different axion fermion coupling that make up this fermion loop. If you step away from this yellow band, for example, you go to explore other regions of the parameter space away from this yellow band, longer probing what's called the QCD axiom, so an axiom that solves the strong CP problem of the QCD sector, but you are probing some axion-like particles, some pseudoscalar boson that have the same physics as the axion. They also couple to the photon, but they are not solution of the strong CP problem, so they are somehow less interesting in terms of theory. But nevertheless, they could be candidates, and they're somehow easier to explore than the axion, because there is a big gap between the yellow band of the QCD axion and actual results from the scanned parameter space. So experiments look for both of these particles, both the QCD axion and axion-like particles. Horizontal lines here are for axion helioscope. So they look at conversion of axions in the sun. These are like sort of like telescopes that are pointed at the sun, and they wait for the production of these particles coming from the sun, directed toward us, reconverted on Earth into a photon inside a magnetic field, would be the other photon. So these lines do not rely on the assumption that the axion is the dark matter. in the universe. We have already a cast that has already taken this type of data. This is why this is a colored solid area, whereas baby IAXO and ALPS are proposed experiments of this type. I will take data if they will be financed in the future, and they appear here as dashed lines in the sensitivity. In contrast, we have here the Axion haloscope. Assume that the Axion is the dark matter candidate in the halo of the Milky Way. So the sensitivity of these cavities is extremely sensitive on this assumption. You need to assume that the Axion is the dark matter in order to reach this sensitivity. And the way in which these cavities work is by resonantly producing a photon inside this cavity. So these are basically magnetic fields in which the cosmic axion resonantly convert into a pulse, which is getting observed.
Luca, sorry, I have a question.
Sure.
About these actions coming from the sun, is there an expected spectrum for these photons? Because I imagine that the background for photons from the sun is huge. So how do you distinguish?
Well, okay. Yes, there is a expected background. Sorry, there is a spectrum of axions which you can probe. And the fact is that the axions coming from the sun have to be reconverted into photons at Earth inside the magnetic field. So this is a process that is peculiar to the axion. So photons would not interact in the magnetic field to give the same type of signal.
So the magnetic field is the magnetic field of the Earth, not the sun's magnetic field.
Yeah. It's a magnet. So this is the biggest cost of this type of experiments.
Okay. In the
So
lab.
you need to buy a magnet which is tuned to the value of the axion mass, basically, which is in the gigahertz. And then if the axion mass matches the frequency of this magnet in the laboratory, then you can allow for a resonant conversion into a. So this is the signal that you look for.
Oh, I see. Okay.
So these are experiments that take a considerable amount of time because they have to scan different frequencies. They have to tune the cavity in different ranges of the axion mass. This is why it takes years for a certain region or a certain experiment to probe what they can do, what they plan to do. They need to get to the desired sensitivity.
Okay.
And have to manually tune the cavity. So,
excuse me.
Yeah.
Just because you say that the axion has a little mass, right? So how could it provide to be a CDM? Dark matter.
It's a non-thermal mechanism, which I will discuss now. So
okay,
you expect axion to be produced both thermally and non-thermally. The thermal part for such a low mass, so the thermal part would contribute to the energy density, same as neutrinos. So it will not be relevant for this range of masses. Because omega goes like the mass over 100 electron volt. So for this, value of the mass is not relevant. Whereas the non-thermal part can actually be the dark matter in the universe. So let's I explain now how. So if you want to embed your Axion theory, you need to introduce a new complex field, which is called the Pechequin field. So this is it's a complex field in which the axion appears as a phase, scaled by the energy, its energy scale F. And you also have a scalar here, rho. And what you do is actually performing a spontaneous symmetry breaking of this Pechequin field. So the dynamics is very similar to what you expect for the Higgs field. You have a phase transition at the when t is of order f. In this phase transition, the Axion field relaxes. Sorry, the Pechequin field, the radial part of the Pechequin field relaxes toward the zero at a distance f from the center. The axion can be anywhere in this bottleneck, in this bottom of the potential. So it takes any value between 0 and 2 pi. Now you have an additional mechanism at much smaller temperature. So when universe from being in temperature of order Fa gets to order the QCD phase transition, you have additional effects that come from the non-trivial vacuum structure of the QCD that feed back on the Axion field and provide it with an additional potential, which can be pictured as a tilting of this Mexican hat potential. So the Axion could sit anywhere between minus pi and pi here, but due to the QCD effect, this tilted Mexican hat would make the Axion coherently oscillate about the minimum, the true minimum of the theory. And it is these oscillations that store the energy density of the Axion. So you have to think of this particle as a harmonic oscillator, is a classical field that oscillates and stores energy in its oscillations. This is so the energy is stored differently with respect to the WIMP. So if you take a WIMP, its mass basically provides the energy. Some WIMP per unit volume give you the required density, energy density to address the dark matter problem. For the Axion instead, it's the oscillations of the field that store the energy density, not its rest mass alone. If you can be more precise in this, you can actually study the equation of motion of the Axion field. So this is theta. This is the Axion field over F. It's a dimensionless quantity. H is the Hubble rate. And you assume that the potential of the Axion provided by the QCD is a cosine potential here. So in the very early universe, when the Hubble rate is much higher than m, you can neglect the potential. You only have the first two terms. This is Hubble damped evolution of the Axion field. And you see that a solution of this equation is just theta equal to 0. So numerically, if you solve this equation, you see that when the Hubble rate is higher than m, theta does not evolve, the Axion field does not evolve, and rho, the energy density associated to it, is approximately constant. So this is a dark energy-like equation of state. But then when H is of order m, so when the temperature of the universe drops so that this condition is satisfied, the potential of the Axion field can no longer be neglected, and this sets into motion the Axion field that starts its classical oscillations. The energy density is then stored in this oscillation, and if you compute it, the energy density scales as 1 over the inverse, as the 1 over the volume, the Hubble volume of the universe. So R here is the scale factor. This is precisely the relation that you look for when you want your dark matter solution, your dark matter particle to address the dark matter issue. And this is why you can have cold dark matter in the form of axions.
Luca, just a quick question. The field oscillates in the late time region, but the energy density oscillates also, or not?
Yeah. This rho is actually rho time average.
Oh, okay.
Yeah, just that the time average, the time over which the Axion field oscillates is much smaller than the Hubble time scale. Below this oscillate. So when it starts to oscillate, then it rapidly starts to oscillate faster than the Hubble time.
Okay,
You
so
can approximate, yeah, you can
basically the average, essentially. Okay.
Yeah, it's time average that is meaningful because the typical frequency is larger than
Okay.
after T oscillation. And this T oscillation is somehow related, is linked to the temperature at which you have the QCD phase transition. So T-os is of the same order as T QCD. Okay, now let's see how the different models in which the Axion field can be the dark matter today. Here I have put F, or equivalently M, on the y-axis. On the x-axis, I've put HI, which is the Hubble rate at the end of inflation. Equivalently, for single field inflation, I expect I can relate HI to the tensor to scalaration. So why HI comes into play? Because we don't know when the QCD phase transition takes place. Sorry, we don't know when the Peccei-Quinn phase transition takes place, because that depends on the value of F. We know that F is somehow larger than a few 10 to the 8, but we don't know its exact value. So the relative value between F A and the Hubble scale of inflation gives us different pictures. Basically, if the Axion field is already present during inflation, we are on this corner of the plot, in which this region is allowed. So in this corner of the plot, the Peccei-Quinn transition occurs during inflation. The Axion field participates in inflation. This makes Axion isocurvature fluctuations important. So your Axion field fluctuates independently from has a component of fluctuation which is independent from the plasma. And this would imprint isocurvature fluctuations, which we do not observe in the CMB. This makes it possible to set a bound on the parameter space of the axiom, which is quite stringent. So we know that HI has to be smaller than 10 to the 9 GeV in order for the axion to be a candidate in this scenario. So this can be. So we need to build a model of inflation which produces such a low value of the tensor to scalar ratio or such a low value of HI in comparison to the value that you observe, that you expect from, for example, chaotic inflation, which is of order 10 to the 13. Alternatively, you can build up models in which you have an isocurvature suppression. So this bound is not so stringent, and it opens up. This has also been is a path that has also been taken in the literature. So why we have a tilt here in the axion isocurvature fluctuation? This is due to the fact that your axion field, which is called here theta I. This is the initial value of the axion field, the value basically of the field that the axion field takes over the unit circle. Here it becomes of order 1, and basically here the axion field starts to probe the non-harmonic term in the cosine potential. So this tilt is due to the non-harmonic part. So basically, as you see, we have a one-to-one relation between the value of f, or the value of the axion mass, and the value of the initial condition theta. The larger the value of f, the smallest, the more I have to fine-tune the initial condition in order to achieve this value of f. If I expect theta to be of order 1, f scales to be of order 10 to the 11. So this is sort of the natural value of f that I expect in the theory. F of order 10 to the 11, or equivalently, m of order 10 to 100 micro electron volt. This also poses some questions for model builders, because this value of f does not seem to be related to the gut scale, which is at much higher value of energy scale, which is 10 to the 15 to the 16 GeV. So we have 4 or 5 orders of magnitude between the Peccei-Quinn phase transition and grand unification theory scale, which also has to be addressed in this model. On the other corner, we have the following. First, we have inflation, and then we have the Peccei-Quinn symmetry breaking. So inflation is left out of the picture. In this case, the axion field has to take the value which lies on the mass of the axion field has to take the value which lies on the dashed line. If it's heavier than this, the axion is a subdominant dark matter component. So if it's too heavy, we need another dark matter candidate that mixes with the axion energy density, and otherwise there is not enough dark matter as what we observe. The point is that in this scenario is extremely difficult to compute, to assess, because of the appearance of topological defects like strings and walls that are associated with the spontaneous symmetry breaking of global U1 symmetry like the Peccei-Quinn symmetry. This has been studied in recent years. So, it's known as the Kibble mechanism, but for the axion field, this has been assessed in the last 10 years with sufficient precision. So what I've plotted here is a slice of a 3D simulation in which the axion field evolves. These colors range from minus pi, which is 0, goes through the minus pi, which is white, goes through the 0 of the axion field, which is in black, and then gets back to pi, taking all values between them. As the axion field evolves, we see the emergence of some regions, of some dots, in which the axion field encircle, ranging between minus pi and pi continuously. This encircle this dot. This is a dot in a 2D slice of a 3D simulation. So this is actually a line in the 3D space, which goes under the name of a global string or axionic string, since we're talking about axions. This is a tubular energy density. Shows its own dynamics. It intersects, connects, and vibrates with other strings, and in its vibration releases a spectrum of axions, including cold axions. So decay of this type of topological structures is another source of cold axion, which cannot be neglected. It gives order same amount as the mechanism that I mentioned earlier. So you expect axions to be formed both from misalignment mechanism and from the decay of these strings, of these topological defects.
So, Luca, in this scenario, strings form first, and then the domain walls form at a lower temperature.
Yeah, exactly. Yeah. So the strings form as soon as you have the Peche-Queen phase transition. So they form at around above 10 to the 9 GeV at the value of F8. Then they evolve down to the QCD phase transition, in which you also form domain walls.
Okay, so and you have to make these domain walls disappear somehow, right?
It depends on the axion theory. So there are ways in which you can embed the axion theory into the standard model. For some models, the domain walls also disappear within a Hubble time, so they're not a problem. In other models, they do not disappear, so they would come to dominate the expansion rate to date, and you have to force them to disappear. You have to make them disappear in numerical simulations by adding some extra.
So
yes.
you have to put by hand some terms that makes them disappear.
Sorry?
You have to put by hand some terms in the Lagrangian to make them disappear.
Yeah, exactly. In some theories in which you have long-lived domain walls, you have to manually make these walls disappear.
Okay.
Yeah. This is not required in all Axion models, but in some Axion models. It's a problem. And it basically depends on how many zeros the axion field takes, the potential takes between minus pi and pi. If there is just 1 0, like in this case, there's no problem. Otherwise, the domain walls do not dissipate so easily. And you need extra features. So let's come to the compact objects, where I might work with Javier Redondo. So in this scenario, so I'll just focus on the scenario in which we leave inflation apart, and then the Pacheco symmetry forms breaks afterwards. This is a scenario in which we have, as we saw, large inhomogeneities in the axion field. So in this box, this box shows the x and y axis is a slice, a 2D slice of the box. The z-axis is the energy density associated with each portion of the box. And we see there are spikes in the energy density, in which the average density in the spikes is much larger than the average density of the box. These are the seeds of what's called Axion mini-cluster. So this overdensity will persist to matter radiation equality. At matter radiation equality, they would enter a nonlinear regime. The gravity would become important, and they would collapse to form gravity-bound objects. They're called Axion mini-clusters. These are dense objects that should persist to date, and they have a typical mass which is in the asteroid mass size. This is ordered as the mass of axions enclosed at the QCD phase transition, because these seeds are formed at the QCD phase transition, and they have a typical radius that's of the order of the Earth to Sun distance. So this is an object. It's like an asteroid spread out over the Earth to Sun distance. Nevertheless, this energy density is still 10 to the 5 to 10 to the 6 times larger than the ambient and the local density of dark matter. So it's a overdensity. The idea is to now to look for effects of the Earth passing through these objects, or other features that could be interesting because of the presence of these objects in the Milky Way. So embodied simulations, recent embodied simulations have shown how the distribution of axion mini-clusters in a galaxy like Milky Way would occur. And in particular, they have come up with what's called the halo mass function. So the number of axion mini-clusters per range of mass per each of these structures. So the mass that I mentioned earlier, this 10 to the minus 11 solar masses, is actually a cutoff, upper bound on the mass of the axion mini-clusters. We expect these structures to be formed with all masses up to this cutoff at the moment of matter radiation equality. But then, after that, you enter the matter-dominated era. You have a structure formation. These axion mini-clusters would also start to clump together and form larger objects, as observed in embodied simulations. The question now is, well, what's the effect of stars? The simulation that I showed earlier just shows, just taking into account dark matter axions in our galaxy without taking into account baryons and stars, which are also present. Since the axion mini-cluster is such a fluffy structure, it's likely that a passing near a nearby star with a sufficiently small impact parameter would deposit enough energy so that it tidally disrupts the axion mini-cluster. Of course, you expect this phenomenon to be more present in the inner orbits of a galaxy. So you expect that the bulge, the inner parts of a galaxy to be depleted of Axion miniclusters, just because there are more stars here. The density of stars is higher. Then, as you move away from the galactic center, you have less and less Axion miniclusters. Sorry, your chance of disruption gets smaller and smaller. You have more and more, larger and larger population of Axion miniclusters. This is what I'm doing now with my supervisor, Christoph Weniger, and two collaborators. We're also in Amsterdam, Thomas Edward, now in Stockholm, and Bradley Kavanagh in Spain. So we took the Hale mass function that's hinted from the n-body simulation, so which expects basically the number of Axion minicluster that populates some logarithmic mass range to drop as with this power law, and we fitted that into a Monte Carlo simulation in which we simulate the deposition of energy due to the nearby stars, so that basically the disruption of the Axion minicluster is controlled by the binding energy of the Axion minicluster itself. If a star deposits some energy density below this amount, below the binding energy of the Axion itself, it strips away some of the outer part of Axions and puff up the structure. Is larger and less massive, so less dense. Whereas if the energy deposition or the encounter of the star with the Axion minicluster is too close, then the star would completely disrupt the Axion minicluster in just one passage. And you basically remove this bound structure. The Axions would then become part of the ambient cosmic population. This is our preliminary result, in which we have taken into account different profiles of the Axion minicluster itself. So this power law, or NFW, which are in blue and in orange, are the results of the survival probability as a function of the semi-major axis of the orbit of the Axion minicluster for Axion miniclusters that show inner density profile, which is power law, which is what you expect from self-similar accretion. So this is the profile that lighter miniclusters would probably show in reality, because they were formed earlier in the universe. Or for Axion miniclusters, they have an NFW profile. So they are formed through hierarchical structure formation. We cannot discern between these two populations, these different profiles, because you would need a even more powerful simulation, n-body simulation, than what I showed earlier. You have to actually see the lighter minicluster have a power law simulation, power law distribution, and distribution when they're heavier. But this simulation are not available yet. We also included the effects of the eccentricity, which is the solid result, with respect to circular orbits, which is the dash results. Of course, for eccentric orbit, you have a lower value of the survival probability with respect to the circular counterpart, because in an Axion minicluster in an eccentric orbit would spend some of its time closer to the galactic center, so in a region with more populated, with a region which is more populated of star. So there are more chances to get disrupted. I would like to mention that this is a result that is not in the literature yet, and the only thing that we know for now is that most of the Axion mini-cluster should survive to date in the case in which there are circular orbits and in the case of power law. So the only thing that is now in the literature is basically a Taylor expansion around this dotted line, which is the position of the solar system in the galactic center, around 8.3 kiloparsec. So as we see, as we expected, the survival probability drops to 0 near the galactic center, and it gets to 1 in the outer regions of the Milky Way. The important part is that nearby the solar system, so nearby this dashed line, even in the worst case of NFW, which is a profile which is more fluffy, so it's much easier to strip these Axion mini-clusters. But even in this worst case scenario, we still have around 30% of the Axion mini-clusters have survived to date with respect to the initial population. So we could still see a significant fraction of effects from this population. This is the same plot, just in different. So this is the galactocentric radius in parsec. And on the y-axis, I've put the energy density of Axion mini-clusters in unit of solar masses per parsec cube. So NFW here is the distribution of Axion mini-clusters in the galaxy. So depending, this NFW would be what we expect, how we expect the Axion mini-clusters to be distributed, like the cold dark matter. This line, which reaches a sort of plateau, is instead the actual distribution of Axion mini-clusters after we have taken into account the tidal stripping. So it's basically NFW in the outer skirt, but then it flattens out because we start to remove Axion mini-clusters due to the interaction with the stars. Now, let's see some applications. This is not from a paper of mine. This is from Farban and other from 3 years ago. They did not take into account the disruption, but they took into account the halo mass function. They semi-analytically computed the halo mass function without embodied simulation, obtaining results that are in fair agreement with embodied simulations. And then they looked at different microlensing techniques. So HAC, that looks at Andromeda and Eros. Here on the plot, they have the fraction of Axion dark matter, which is in Axion mini-cluster. So this fraction cannot be larger than 1, versus the Axion mass. And they set as a target for the Axion mass as the QCD Axion as the dark matter 10 to the minus 4. So 100 microelectron volt. We see that for this N 3.34 is the QCD Axion, is what you obtain for the QCD Axion. What you basically can say is that if there are Axion mini-clusters in the galaxy, they would produce microlensing events if the fraction of Axion mini-cluster is larger than 10%. So if more than 10% of the dark matter Axion is in form of bound structures, then we would observe these effects. So this is a sort of upper limit in the literature from how many of these objects are around today. Another project in which I am involved is Axion radioastronomy. So let's step back for 1 second from the Axion Miniclusters, and let's just consider cosmic axions. Sorry, I thought I closed Skype. Let me close it. Sorry for this. So, neutron stars possess a strong magnetic field. Basically, they would act as cavities. They would convert axion dark matter into a radio signal, since the axion is in the gigahertz frequency. This radio signal could be detected on Earth by looking at target neutron stars. So this is possible because the neutron star, a spinning neutron star, has some plasma around it that creates the condition for having axion photon conversion. This is possible when the plasma frequency, which is a function of the magnetic field, is of the same order of m, of the mass of the axion. So this is a narrow shell around the neutron star in which this conversion is possible. And the idea is to look at some neutron star in which is rotating around some z-axis and has some magnetic field not necessarily oriented to the rotation axis. This group has been able, with this technique, to place an upper bound an upper bound on the axion photon coupling, so the same coupling that I mentioned in my introduction, as a function of the axion mass. So this bound is not sensitive enough to reach the QCD axion line. Nevertheless, it's an independent result with respect to the more conventional cavity searches. What we want to do is the same, but not looking at individual neutron stars that convert dark matter axions, but stochastic source in which neutron stars from our Milky Way galaxy collide with Axion Miniclusters. So this is what we are doing now, is radioastronomy with Axion Miniclusters. What we find is that most of the encounters between Axion Minicluster and neutron stars are concentrated on the galactic disk. This is because that's where most of the neutron stars are found. They are concentrated in a donut, in a ring-like shape on the galactic disk. This is why in the galactic center we do not have Axion Miniclusters anymore, so we cannot have events. And in the outer skirt of the Milky Way, we don't have enough neutron star and Axion Miniclusters, so their number density drops. So we select, basically this selects sort of ideal distance, which is of the order of the 5 kiloparsec, so not far from us, in which you have you maximize this conversion rate. This is the result that we find. So this is also preliminary. If you do not consider tidal stripping, you find the results in orange. You have some peak flux that can be observed, which is comparable to the flux that you would obtain from looking at a single neutron star converting dark matter axions. So this Axion Minicluster radioastronomy is likely a good technique. This is why we are exploring it, that should lead to interesting results in the future. On the x-axis, we have put the encounter duration, so how much time the flying neutron star spends inside the Axion Minicluster? Or how long does this encounter last? Or how long should the signal be seen? The effect of the tidal stripping is basically that of removing the part of the plot in which we have the longer encounter duration here. This is because longer duration is related to bigger Axion Miniclusters. They have a larger radius, so the neutron star spends more time in that. But they are also more easily stripped away. So this is why this part is removed from the stripping with ordinary stars. These Axion Miniclusters are removed of some of their mass, they are puffed up, and they end up in this second population here, which give rise to a much lower and not detectable flux. Whereas we still have some portion of the original population, which yields to a detectable signal. This is still under discussion, though, especially how the technique that would allow us to do so, is what we are working on now. Now, let's come to another topic, which is Axion stars. So, inside Axion Miniclusters, there are the conditions for the formation of an even more exotic product, which is called the Axion star. This is basically a Bose-Einstein condensate. Axions are boson, they can condensate. They can lose energy through the so-called gravitational cooling, which is this paper here. Whereas this picture is from LEVC of 2016, in which they numerically show that gravitational cooling is possible. So the inner part of the Axion Minicluster would have the conditions for which the axions that make there lose so much energy that they all fall into the lowest energy level. So an Axion star is basically a particle in a box. You know that it has some extent r, so the boson inside of it has some wavelength, which is comparable to the size of the box, and it has some momentum associated with it because of the uncertainty principle. Also, it has a mass, which is given by the number of axions in the Axion stars times the mass of the individual axion. We can then define inner energy, internal energy U, which is given by the kinetic energy associated to the Heisenberg uncertainty principle, the self-gravity term, which goes with the mass square of the star itself, and the quartic self-interaction, which comes from the, a potential term which is proportional to the quartic self-interaction. So this term is entirely due to the axion-axion interaction with itself. And we look at the equilibrium solution, so the solution for which the gradient of the potential is 0. Let's see what we find. In order to do so, we actually perform a more sophisticated method in which we solve for the Schrödinger equation of the individual axion. And we look for the solution that look like a solid, which means that it's a localized solution in which the axion field takes its maximum value at the center of the axion star, and then it drops to 0 in the outer region. The mass is then equal to the mass of the energy density below this solution, and the radius is equivalent to the region that encloses 90% of the mass of the axion. star. Okay, this is what I've done with my collaborators. Again, Javier, Katie Fries was my supervisor. Spasma was a PhD student in Stockholm. Now he's in Stanford, and Frank Wilczek. So what we studied here in this plot is the radius of the Axion star, rescaled in units of 1 over the mass of the Axion, as a function of the rescaled mass of the Axion star in these natural Lagrangian. So let's focus on this blue line, which is the line that you obtain for f equal to the 11 GeV. So more or less what you expect for the QCD Axion. This equilibrium here, this defines the equilibrium line in which you would obtain an Axion star. This is set only by the interplay between the pressure due to the Heisenberg uncertainty and gravity. So self does not take any role. You have some Axions move due to the uncertainty principle. The star is held together because of gravity. The line here is parametrized. So the inner parameter is the density. The more dense the Axion star, the more I move along this arrow. At some points, you hit some critical density in which your quartic self-interaction can no longer be neglected. This defines a new regime in which the gravity, which is attractive, is replaced by self-interaction, which is also attractive. We see that now we enter in this new regime, which is this dashed red line. Here, basically at this kink, we have an upper limit for the Axion stars to have a mass higher than this. We also don't expect densities higher than this corner because all of this red line here, so all of these configurations are unstable, which means that if I perturb my configuration here by a little bit, well, the unstable equilibrium would bring the Axion star back to this blue line. So the quartic self-interaction doesn't give you a stable solution, whereas gravity does. So only the blue line can be achieved in nature. It was thought in the past that you could reach a third branch, which is called the dense Axion star. Dense in the sense that not only you probe the profile from the part of the potential coming from the quartic self-interaction, but you probe all of the expansions of the cosine potential of the Axion. We also showed that there is no dense Axion star because in this regime, your Axion become relativistic. So, first of all, the non-relativistic approach of the Schrödinger equation doesn't work anymore, and because the Axions are relativistic in this regime, they would stream away from the Axion star and would basically disrupt it in some finite lifetime. So there is no dense Axion star branch. So the only hope in which to detect Axion stars is through these negative slope branches. Okay, it's 5:15. Do you want me to continue? I have another topic of discussion. Otherwise, I can close. Let me know.
Yeah, you have 5 more minutes.
Okay. Well, then I'll briefly mention work with a master student in Uppsala, which is gravitational waves from strings. So I already discussed about the network of axionic strings that are formed in the early universe, and the fact that they would radiate axions in when they are in closed loops configuration that makes them shrink. The point is that you, as a loop, radiate two different types of radiation. So a global string is expected to lose energy through gravitational waves, in which G is Newton constant, gamma is a factor of order 50, and mu is the energy per unit length of the string. An axionic string would also produce lose energy, or would mainly lose energy in Goldstone boson, where K is another parameter of order 50. And we see that basically, since this mu for our axion string is of order f square, here we have G times a relative factor G f square, which is of order f over m Planck, that basically kills the production of gravitational waves in axionic strings. So the production of the spectrum of boson is the dominant mechanism of decay for the axionic strings. Another difference between a global string network and an axionic string is that the axionic string network is dissipated when the axion fields start to oscillate because of the formation of the main walls. Whereas a global string network might persist to present day. Now, is it possible to find configurations in which this part is also relevant? Yes, if you find a way to increase your mu. This is what happens in non-standard cosmologies. So the idea is that in a cosmological setting, we start from the Planck era, and then we have our universe that cools down. It goes through a series of phase transitions, gets into the nucleosynthesis part, which is the important one because we cannot touch it. But we also don't know what's above the nucleosynthesis. So we have a reconstruction of the universe through relics, through Big Bang nucleosynthesis, up to 3 minutes after the Big Bang, but we don't know. This is a black box. Is the lambda CDM model valid here? We don't know. So there is some maximum temperature above which we might think about a non-standard cosmology. We might think that our universe was dominated by some other form of energy other than radiation. We have other hints. What we are looking basically is a relic, dark matter, baryogenesis, gravitational waves, something that tells us what was the main contributor of the cosmology prior 3 minutes after Big Bang. So in this spirit, we consider different cosmological setting. If you take the global string network that I mentioned earlier, it just a string network that just decays through gravitational waves is persistent to date in lambda CDM, gives rise to this solid black line. So a spectrum of gravitational waves as a function of the frequencies that can be observed, which is within reach of the future observers. If your Tmax, so if you have lambda CDM holding up to, for example, 1 GeV, and then you have matter domination above that scale again, because you have some massive relic from inflation, well, then your spectrum of gravitational waves would depart from the standard, the expectation from the standard cosmological scenario, and would instead take this slope. This is what we observe also for the Axion. This is what I've done with a master student, Niklas Ramberg from Uppsala. We show that, well, you have to go to much lower reheat maximum temperature. So you have to push to the limits allowed by the Big Bang nucleosynthesis, which is of the order of 1 MeV. But in this extreme exotic scenario, in which you have a matter-dominated universe that lasts until around 1 MeV, you can produce a spectrum of gravitational wave, which is within reach of the future detectors. Of course, this is an unlikely scenario because of a number of factors. For example, how do you build the baryogenesis in this model? More likely scenarios would not allow for this and would then predict a much smaller value of gravitational waves from this scenario. So basically, the bottom line is that in general, gravitational waves from axionic strings are extremely unlikely to be detected in the future. And this is a result which is solid in different non-standard cosmological results. Okay, so these are my conclusions. Mainly the fact that Axion Miniclusters and Axion stars are laboratories that we need to exploit in order to probe physics that lies beyond the standard model. Thanks.
Thank you, Luca, for this nice presentation. Now we have questions. I'm going to start with some questions from Parisa.
Okay.
Her microphone is not going to be recorded, so I'll read her questions. So, one question. Can we expect a flux of photon coming from the Miniclusters?
Yeah. Well, yes.
Okay.
You expect a flux of photons, for example, in the terms of radio signals, which is what we are trying to observe when the Axion cluster goes through the magnetic field of a neutron star. So that's one example. Another example could be, for example, including the axion photon coupling. Density of an Axion cluster is low, but people have shown that for Axion stars, this would be important. So, yes, this would be a extremely small radio signal that would basically come out of the Axion star population.
Okay.
Because basically these are bound with dense lump Axion. In this case, no Axion photon conversion or Axion. Yeah, Axion photon conversion would be.
Okay. So about these Axion Miniclusters, I have a question myself. What causes the disruption of these Miniclusters? I don't get it.
The gravitational interaction with stars, ordinary
So you
stars.
have a star passing close to the.
Yeah.
Okay.
Yeah. This is what we are simulating now. Just a mini cluster is much less massive than a star. So, and it's very hot, so it's easy to have axions stripped away from that.
So another question from Clarissa. Since we have this decrease in the dark matter density in the galactic center, we avoid the dark matter explanation to the galactic center axis?
No, not really. Let me go to the slide. The point is that this is only the profile in Axion mini cluster. So the NFW from so this is a sort of mixed dark matter selection, which most of the dark matter is in unbound cosmic axions, and some matter is in these Axion Miniclusters. So this profile is only the profile of Axion Miniclusters. But the NFW profile would hold for the cosmic axion to the galactic center.
Okay, okay, I see. A final question from Clarissa is, what's the average fraction of dark matter that the axion can be? I think in one of that scenarios in which dark axions can be a fraction of dark matter, of the total amount of dark matter, she asks, what's the average fraction of the dark matter which axions could constitute?
Ah, okay. Well, I would say in general here you can range any fraction. The more massive it is, the more subdominant. You can take a specific model. For example, note that there are a couple of papers that have looked for axions embedding supersymmetry. So in this case, you have axion and WIMP, which make a mixed dark matter model, in which the WIMP is the main dark matter component, but you can scan the parameter space so that you see also which fraction is made of axions. I don't remember what's the outcome of it, but I can send the links for that. But basically, the answer is that it would depend on the model that you study. There are some specific models, SUSY, that have been studied. And in the SUSY, you also have other candidates, which are called Axino and Saxion. So the Axion is associated to a complex color field. So these are 2 degrees of freedom. And if you supersymmetrize it, you get 2 additional degrees of freedom that can also or as that radiation.
Okay, but in general, it is model dependent.
Yes, in general, it's model dependent.
Okay. So, okay, any other questions from the audience? I have another question. In one of the plots, you showed I think that it was the field, the action in an action star. It decreased, and then at some point, it seemed to become negative.
Here?
In the previous slide.
Here? No.
No, maybe, yes, this one.
Okay, so
this negative value, there is any special meaning?
So this is well, this is theta. So this is the value of the field. The energy density would be the square of it.
Yeah.
The point is that what we are looking for here is for a solution which is finite at the center and 0 at infinity. This is called solving the Schrödinger equation by Schrödinger. So you take different initial conditions, and you look at the initial condition that also satisfies the boundary at infinity.
So these solutions which become negative don't satisfy the equation?
Exactly. Yeah, they don't satisfy the boundary condition of the Schrödinger equation. So you only take the solution that drops to 0 at infinity.
Oh, okay.
Yeah.
So only those solutions can correspond to actual axion stars?
Yes, exactly. They are solitons. They are soliton solutions of the Schrödinger equation. Exactly.
Okay. Any other questions? Yes. No? So, okay. So let me thank you again, Luca.
Yeah, thanks.
Many thanks for your presentation.
Yeah, it was very nice. Thanks for the many questions.
Okay, so I think we can stop here. Thank
Okay.
you all guys for your audience. See you next time.
Okay. Thanks for the attendance. Bye.
Okay. Bye guys.
Bye bye.